Have you ever looked at a p value and thought, what even is this thing? Or worse, thought it means your hypothesis is 95% true? Yeah, most people do. And that one tiny misunderstanding has wrecked countless research papers, medical studies, and even election predictions. Most people think a p value tells you the probability that your hypothesis is true. It doesn't. Students get confused, researchers misuse it, and even some professionals explain it wrongly. But today, I'll show you what a p value really means using the simplest explanation you've ever heard. First, let's clear something up. A p value is not the probability that your hypothesis is true. It's also not the probability that your result happened by accident. And it's definitely not the chance your research is correct. All of those definitions are wrong, but very common. Here's the correct meaning. A p value is the probability of getting your observed result, or something more extreme, if the null hypothesis were actually true. Let me repeat that in simple English. Assume nothing interesting is happening. If we repeat the experiment many times, how unusual is the result we got? That unusualness is the p value. Before the 1920s, statistics had no standard way to answer the question: is this result just luck, or is something real happening? Scientists often relied on judgment, vague significance ideas, or subjective arguments. There was no common threshold and no widely accepted framework until 1925. In his famous book, Statistical Methods for Research Workers by Sir Ronald Aylmer Fisher, Fisher introduced the p value as a measure of how surprising your data is if the null hypothesis were true. He said researchers should compare the p value to a conventional cutoff, such as 0.05, to judge statistical significance. Fisher did not believe in rigid decision rules of accept or reject the null hypothesis. Instead, he believed p value equals strength of evidence. Smaller p value equals stronger evidence against a null hypothesis. This is how p value was born. Imagine I give you a coin and claim it's fair. You flip it 10 times and get 9 heads. Is the coin fair or suspicious? If the coin were truly fair, the chance of getting 9 or more heads out of 10 flips is very small. The result can be obtained using the binomial probability distribution function, which gives 0.0097, about 1%. So the p value is 0.01. This means if the coin is really fair, such a result is extremely unlikely. Let's explore other scenario. If the class average is 60, you scored 85. The question is this just luck, or are you genuinely better than average? How p value fits null hypothesis: you are an average student, or in a more statistics term, there is no significant difference between your score and the average score. The p value will be the probability of scoring 85 or higher if you were truly average. If the p value is 0.01, it means only one out of 100 average students would score this high by chance, which indicates you might not be an average student. Let's also look at this example. If a new drug claims to reduce fever faster than the old one, how p value fits? The null hypothesis. The new drug works the same as the old one, or in a more statistics term, there is no significant difference between the new drug and old one. The p-value will be the probability of seeing this improvement if the drug actually does nothing. New. A p-value of 0.03 means there is only a 3% chance would see results this strong if the drug had no real effect. This does not mean the drug works 97% of the time. If a factory claims only 2% of products are defective, you inspect 50 items and find 8 defects. Null hypothesis. Defect rate is still 2%. P-value. Probability of finding 8 or more defects if the factory is telling the truth. If the p-value is tiny, it tells us this many defects is too suspicious to ignore. Let's look at this last scenario. In court, the assumption is the accused is innocent. P-value, probability of seeing this much evidence if the person were truly innocent. A small p-value is like evidence so strong that the jury says this is too unlikely to ignore. This explains why we don't prove, we reject. Now you see why researchers use 0.05 as a cutoff. If the p-value is below 0.05, your result is considered statistically significant. Why 0.05? Honestly, tradition, not mathematics, just history. But it works as a useful threshold for most analysis. Suppose we want to test if a new teaching method improves exam scores. We take two small groups, control group, treatment group. We run a t-test and the p-value comes out to 0.012. Here's what that means. If there is no real difference between the teaching methods, then getting a difference this large between the two groups would only happen 1.2% of the time. That's pretty rare. So we say the result is statistically significant. Now the important part, because people misuse p-values every day. A p-value does not tell you the size of the effect, whether the effect is important, the probability the null hypothesis is true, the probability the alternative hypothesis is true, whether your study is well designed. A p-value only tells you how unusual your result is under the assumption of no effect. That's all. Here's the simple takeaway. 1. Assume the null hypothesis is true. 2. Check how unusual your result is. 3. That probability is your p-value. Small p-value equals unusual equals evidence against the null. That's it. Clean and simple. Thank you for watching.